Welcome to Royal Research. When building complex robots, success depends on the ability of individual software components to share data and instructions flawlessly. By the end of this guide, you will write and run custom Python nodes that communicate using the two primary ROS pipelines, topics and services. To follow along, ensure you have an active ROS1 installation, a pre-created workspace package, and your code editor ready. Mastering these foundational communication networks is what allows separate, modular scripts to function together as a single coordinated system. Every ROS environment starts with the ROS master. This acts as the central registry, a switchboard that allows all distinct nodes in your system to find and talk to one another. Open your first terminal window and execute the command roscore. This boots up the master registry. Watch the terminal for a line reading started core service along with the ROS URI. This confirms the master is successfully launched and actively running. You must leave this specific terminal tab open in the background. If you close it, all subsequent node communication will fail. With the master awake, the robot's internal switchboard is now ready to route data traffic between your nodes. The publisher-subscriber model handles continuous asynchronous data broadcasting over a named channel called a topic. To build this, create a new Python script for your publisher node and configure it to broadcast on a specific topic named /chatter. The rospy.publisher line in your script defines the data type, in this case a standard string, and initiates the outgoing broadcast. Next, create a Python script for the subscriber node designed to listen to that exact /chatter topic. Inside is a callback function. This block of code is automatically triggered every time a new message arrives from the topic. Before running these files, make both Python scripts executable in Linux by using the chmod +x command in your terminal. Open two new terminal windows and use the rosrun command with your package name to launch the talker and listener scripts. You can verify the connection by checking the terminal output. Matching timestamps are highlighted across both windows to prove that data is successfully moving between the scripts. This fire and forget model is the standard architecture for handling continuous data streams, such as live camera feeds or sensor readings from wheel encoders. Some situations require precise synchronous one-off commands. In ROS, we handle these specific request and reply interactions using services. To set up a service, you first create a .srv file. This file structure strictly separates the input variables from the expected output response. Now, write the server node Python script. This node acts as a standby listener, waiting for a math request. The rospy.service command registers the node with the ROS master as a valid service provider, making it available for other nodes to call. Next, write the client node script. Unlike a publisher, the client will pause its own operation until the server sends back a reply. The rospy.service proxy command packages the specific request integers, 5 and 7, and sends them to the server. Execute the server script first in one terminal so it is ready to receive. Then run the client script in a separate window. The terminal output confirms success. The client sends the equation and receives the correctly calculated sum of 12. While topics provide a continuous stream, services offer strict control and confirmation, making them ideal for executing discrete, high-stakes actions. You have now successfully built both a continuous asynchronous antistream and a precise synchronous command network from scratch. To test these skills, try modifying your .srv file and scripts to multiply 3 numbers instead of adding 2. Congratulations from Royal Research. To continue developing your engineering skills, subscribe for more advanced robotics tutorials. By combining these two communication pipelines, you have the foundational tools needed to build and organize multi-part robotic systems.